When we look at the Earth from the perspective of its surface, the land masses may look very rugged, as this picture of the very young Andes Mountains suggests. We would see dramatic elevation changes, mountains, canyons, undersea volcanoes. The surface of the Earth compared to the rest of the planet would resemble perhaps an orange with a pimply surface. The thickness of the crust of the Earth would resemble the thickness of the paper glued to the surface of a world globe. These are our learning objectives for Chapter 2. A magnetic field and atmosphere surround our planet. The Earth's system includes many distinct and interacting realms. The Earth has distinct internal layers, crust, mantle, and core. And the Earth has a rigid lithosphere that overlies a plastic asthenosphere. Our journey to the center of the Earth begins out in interstellar space, the region between stars that boasts a vacuum so profound that it contains less than 1 atom per liter. By comparison, air at sea level contains about 2.7 times 10 to the 22 atoms per liter. The atoms in interstellar space may be leftovers of the Big Bang, or they may be cosmic rays, high-energy atomic nuclei ejected into space at extreme velocity by supernova explosions. Eventually, our spaceship begins to feel the ever-so-weak pull of the sun's gravity. This happens at a distance of about 50,000 AU from the sun. An AU, or astronomical unit, is the distance between the Earth and the sun, and it equals about 150 million kilometers. As it continues to move towards the sun, the exoprobe detects specks, flakes, and balls of ice, either leftovers of the nebula from which our solar system formed or fragments scattered into space soon after its formation. Together, these objects make up the Oort cloud, O-O-R-T cloud, whose inner edge lies at a distance of about 3,500 AU from the sun. At a distance of about 200 AU, our spaceship enters the Heliosphere. The region within the Heliosphere contains predominantly solar wind particles, electrons and protons ejected into space from our sun, whereas the region outside contains predominantly cosmic rays ejected from other objects in space towards our sun. The Heliosphere technically defines the edge of the solar system that Voyager 1 crossed in 2013. At a distance of 30 to 55 AU, our spaceship traverses the Kuiper Belt, a diffuse ring of icy objects that once formed the outer reaches of a protoplanetary disk. About 100,000 of the objects in the Kuiper Belt have diameters over 100 kilometers, and some such as Pluto and Eris have diameters of over 400 kilometers and are known as dwarf planets. Comets originate from the Kuiper Belt and to a lesser extent from the Oort cloud. All told, the Kuiper Belt and Oort cloud could contain 1 trillion objects with a combined mass that may approach that of Jupiter. The orbit of the ice giant Neptune, our solar system's outermost true planet, defines the inner edge of the Kuiper Belt. Once we've passed this orbit, we're traversing interplanetary space. In interplanetary space, the concentration of atoms increases to between 5,000 and 100,000 per liter. So while the region still represents a profound vacuum, it is much denser than interstellar space. As we zoom across the plane containing the orbits of all the planets, it passes Uranus, the second ice giant planet, the 2 gas giant planets Saturn and Jupiter, and the asteroid belt, a diffuse band about 2.5 AU across that contains about 10 million small solid objects. In the inner part of the solar system, we find the 4 terrestrial planets: Mars, reddish Mars, bluish Earth with its large moon, green and greenish cloud enshroud Venus, and heavily cratered Mercury. As our ship nears Earth, we begin to detect a magnetic field. A magnetic field is the region measurably affected by the force emanating from a magnet. This force, which grows progressively stronger closer to the magnet, can cause another magnet or charged particles to move. The Earth's magnetic field, like the magnetic field around a familiar bar magnet, is a dipole, meaning that it has 2 ends, a north pole and a south pole. If you bring 2 magnets close to each other, the unlike poles pull towards each other, and the like poles repel or push away from each other. By convention, physicists represent the orientation of a magnetic dipole by an arrow that points from the south pole to the north pole, and they depict the magnetic field of a magnet by a set of invisible magnetic field lines that curve around the space around the magnet. The figure on the left. Arrowheads along these lines point in a direction to complete a loop. Magnetized materials such as iron filings or compass needles, when placed in a magnetic field, align with the field lines. Because it is dipolar, we can simplistically represent the Earth's magnetic field as emanating from an imaginary bar magnet in the planet's interior, the figure on the right. The north pole of this bar, as defined by physicists, lies near the south geographic pole of the Earth, whereas the south pole of the bar lies near the north geographic pole. The geographic poles are the places where the Earth's axis of rotation intersects the planet's surface. Presently, the axis tilts at an angle of about 23.4 degrees 23.4 minutes relative to the plane of the Earth's orbit. That's 23.4 degrees relative to the plane of the Earth's orbits. Geologists and geographers, by convention, refer to the magnetic pole closer to the north geographic pole as the north magnetic pole, and to the magnetic pole closer to the south geographic pole as the south magnetic pole. This way, the north-seeking end of the compass needle points towards the north geographic pole. Although the magnetic field behaves like a dipole, the field lines are distorted by the solar wind into a teardrop pointed away from the sun. The magnetic shield protects Earth life by deflecting harmful solar radiation. The region inside this magnetic shield is called the magnetosphere. A secondary line of defense called the Van Allen radiation belt exists from 3,000 to 10,500 kilometers out from the Earth. The magnetic field is stronger inside this region and traps both cosmic winds and solar winds that are moving fast enough to penetrate the outer, weaker part of the magnetosphere. Still, some particles penetrate the Van Allen belt and follow magnetic field lines to the polar regions of the Earth. When these particles react with gas particles of our atmosphere, they begin to glow, forming the aurora borealis of the north and the aurora australis of the south. When our spaceship descends to an elevation of 600 kilometers or 370 miles, it encounters the Earth's atmosphere. 99% of the Earth's atmosphere is nitrogen and oxygen, N2 and O2. 78% of our atmosphere is nitrogen and 21% is oxygen or O2. Trace gases total less than 1%. The trace gases are argon, carbon dioxide, neon, methane, ozone, carbon monoxide, and sulfur dioxide. The density of the atmosphere progressively increases as we get closer to the Earth due to the weight of overlying air squeezing and compacting the air below. The density of the innermost terrestrial planets vary in density. The density of Earth atmosphere is 1.2 grams per liter. The density of Venus is a whopping 6.5 grams per liter. Density of Mars atmosphere is about 0.02 grams per liter, and the density of Mercury's atmosphere is 10 to the minus 14 grams per liter. The density of the atmosphere progressively increases closer to the Earth, for the weight of overlying air squeezes down on the air below, pushing gas molecules in the air closer together. At the Earth's surface, molecules are close enough together that the atmosphere has a density of 1.2 grams per liter. While vastly greater than that of interplanetary space, this density is only 12% that of water. Air pressure, the amount of push that air exerts on materials surrounding it, also increases closer to the surface because of the weight of the overlying atmosphere. Technically, we specify pressure in units of force per unit area. For example, we could specify atmospheric pressure in pounds per square inch or kilograms per square centimeter. Air pressure at sea level averages 14.7 pounds per square inch or 1.04 kilograms per centimeter squared. Researchers generally use other units such as atmospheres, abbreviated ATM, and bars. Air pressure at sea level is 1 atmosphere. An atmosphere and a bar are almost the same. 1 atmosphere equals 1.01 bars. Since air pressure decreases with increasing elevation, the air pressure at the peak of Mount Everest, 8.85 kilometers above sea level, is only 0.3 bars. People can't survive for long at elevations above 5.5 kilometers, where the air pressure is about 0.5 bars, or 50% that at sea level. So since jet planes fly at altitudes above 5.5 kilometers, their cabins must be pressurized by pumping air in. The decrease in density with elevation means that 99% of atmospheric gas lies at elevations below 50 kilometers, and the atmosphere can barely be detected at elevations above 120 kilometers. While gravity still attracts air molecules to the Earth for half the distance to the Moon, there are so few molecules at elevations above 600 kilometers that the molecules no longer collide and interact like those of a gas. As a consequence, researchers generally consider the top of the atmosphere to lie at about 600 kilometers. Atmospheric scientists divide the atmosphere into layers. Most winds and clouds develop only in the lowest layer, called the troposphere. The troposphere lies between 0 kilometers and 11 kilometers. This is the lower mixing layer. Weather is confined to this layer, and temperature decreases upwards. The next layer is called the stratosphere, which lies 12 to 47 kilometers above the Earth. No mixing occurs within this stratosphere, and temperature increases upwards. The next layer up is the mesosphere, 47 to 82 kilometers. Temperature decreases upwards within this layer. And the final layer is called the thermosphere, which is 82 plus kilometers. This is the outermost layer, and temperature increases upwards in this layer. Each layer is separated by pauses. So between the troposphere and the stratosphere, we have the tropopause. Between the stratosphere and the mesosphere, we have the stratopause. And between the mesosphere and the thermosphere, we have the mesopause. Beneath the atmosphere, which is the gaseous envelope we just discussed, lies the hydrosphere, which is surface and near surface liquid water, the cryosphere, which is surface and near surface ice and snow, the biosphere, which has the greatest variety of living organisms, and the solid Earth. Geologists refer to the combination of these components and the complex interactions among them as the Earth system. Of all the planets in the solar system, only the Earth currently has liquid water, for our planet lies within the habitable zone, the distance from the sun, at which temperatures range between boiling and freezing points of water. On the planets closer to the sun than the habitable zone, all water evaporates, and on planets further away, all water exists only as solid ice. Astronomers estimate that the habitable zone in our solar system extends between 0.8 and 2.5 AU. This region includes the orbits of Earth and Mars and some of the asteroid belts. Venus orbits near the inner edge of the habitable zone. The fact that the surface temperature on Venus are way too hot for life, and those are 460 degrees centigrade, and those on Mars are too cold, minus 55 degrees centigrade, has to do with the respective abilities of their atmosphere to trap heat. Venus has dense atmosphere that traps a lot of heat, and Mars has very thin atmosphere that allows heat to escape. When we look at the Earth's surface from a map, we see that about 30% of the crust is continental and 70% of the crust is marine. The highest point on land, the peak of Mount Everest, lies about 8.9 kilometers above sea level, while the lowest point, the shore of the Dead Sea, lies about 0.4 kilometers below sea level. Most of the sea floor comprises broad abyssal plains, where the flat seafloor lies at a depth of 4 to 5 kilometers below sea level. The seafloor rises to shallower depths along mid-ocean ridges, which are elongate submarine mountain chains that rise as much as 2.5 kilometers above the abyssal plains, and descends at subduction zones to greater depths in deep sea trenches, which are elongate troughs in which the seafloor lies as much as 10.9 kilometers below sea level. The Earth's total relief from the floor of the deepest trench to the peak of the highest mountain is 19.8 kilometers, and that is only 0.3% of the Earth's radius of 6,371 kilometers. The Earth is really a very smooth ball. A graph called a hypsometric curve plots the surface elevation on the vertical axis and the percentage of the Earth's surface on the horizontal axis. Shows that only a relatively small proportion of the Earth's surface occurs at very high elevations, that is, mountainous elevations, or at a great depths along deep sea trenches. In fact, most of the land surface lies within just a kilometer of the sea level, and most of the sea floor lies between 4 and 5 kilometers deep. Consequently, changes in sea level of tens to a couple of hundred meters would dramatically change the area of dry land. Of the 92 naturally occurring elements produced by fusion reaction in stars and by supernova explosions that make up Earth, 91.2% of the Earth's mass consists of only 4 elements: iron, oxygen, silica, and magnesium. Iron contains about 32.1% of the Earth, oxygen about 30.1%, silicon 15.1%, and magnesium around 13.9%. The ratios change somewhat for the crust and the mantle and the core. Minerals are defined as homogeneous, naturally occurring, solid, inorganic substance with a definable chemical composition and an internal structure characterized by an orderly arrangement of atoms, ions, or molecules in a lattice. A rock is a coherent, naturally occurring solid consisting of an aggregate of minerals. Igneous rocks are rocks that cool and solidify from hot molten magma. Sedimentary rocks are rocks that form either by the cementing together of fragments broken off of pre-existing rocks or by the precipitation of mineral crystals out of water solution at or near the Earth's surface. Metamorphic rocks occur as a result of solid state change that occurs within a pre-existing rock as a result of increase of heat and or pressure. Elements combine in a variety of earth materials to form grains, which are individual mineral crystals, sediment, which is accumulation of loose grains, metals, which is composed of metal ions, melts, solid materials are heated to liquid form, or volatiles, materials that transform into gas. As we have already discovered from our study of igneous and metamorphic rocks, in sedimentary rocks, the deeper that we go within the earth, the greater the pressure is. So the weight of overlying rock increases with depth. And at the Earth's center, pressure probably reaches about 3,600,000 atmospheres. Well, temperature also increases with depth in the Earth, as we found out with igneous rock and also with metamorphic rock. Even on a cool winter's day, miners who chisel away at gold veins exposed in tunnels 3.2 kilometers below the surface swelter in temperatures of about 53 degrees centigrade. We refer to the rate of change in temperature with depth as the geothermal gradient, or geotherm. In the upper part of the crust, the geothermal gradient averages between 15 degrees centigrade and 30 degrees centigrade per kilometer. At greater depths, the rate decreases to about 10 degrees centigrade per kilometer or less. So 32 kilometers below the surface of a continent, the temperature reaches 400 degrees centigrade to 700 degrees centigrade, depending on location. No one has ever directly measured the temperature at the Earth's center, but calculations suggest it may exceed 4,700 degrees centigrade, close to the sun's surface temperature of 5,500 degrees centigrade. In 1776, the British royal astronomer Neville Maskelyne came up with the first realistic estimate of its mass. He obtained this estimate by observing the deflection due to gravitational attraction of a nearby mountain, the Himalayas, of a lead ball called a plumb bob suspended from a wire. Maskelyne reasoned that if the mountain weren't there, the lead ball would be pulled straight down by the Earth's gravity. The mass of the mountain pulled the ball sideways towards it, so the wire made a slight angle relative to vertical. Since Newton's law of gravity states that the strength of gravitational pull depends on the amount of mass present, the amount of deflection represents the mass of the mountain relative to the whole Earth. From his measurement, Maskelyne calculated that the Earth had a density of 4.5 grams per cubic centimeter. In 1798, another British scientist used a different method for measurements and came up with a value of about 5.5 grams per cubic centimeter, the number we use today. Since average rocks at the Earth's surface have a density of only about 3.0 grams per cubic centimeter, researchers immediately realized that the interior of the Earth must contain denser materials than its outermost layer and couldn't possibly be full of caverns or other open spaces. Researchers eventually concluded that this material must be a metal, for only metals could have sufficiently high density. With this idea in mind, they then addressed the question of where the metal of the Earth's interior resides. They realized that since the Earth has the shape of a sphere, the metal must be concentrated near the center. Otherwise, centrifugal forces due to the spin of the Earth on its axis would pull the equator out, and the planet would become somewhat dish-shaped. Laboratory studies show that the immense pressures occurring in the Earth's core, the metal that makes up the core would be almost twice as dense as it is on the Earth's surface because the pressure squeezes molecules closer together. Researchers then wondered about the state of the materials in the Earth. Are they solid or liquid? Eventually, they concluded that even though molten rock occasionally oozed out of the interior at volcanoes and therefore must exist somewhere inside the Earth, most of the interior must be solid because if it weren't, the land surface would rise and fall due to daily tides, much more than it actually does. To understand how earthquakes can provide information about the Earth's interior, we first need to understand what an earthquake is. Most earthquakes happen when rock within the outer portion of the Earth suddenly breaks along a fault, a fracture on which slip occurs, and generates energy that travels through the surrounding rock outward from the break. You can simulate this process on a small scale by snapping a stick between your hands. The shock that you feel is energy that propagated along the stick from the break in your hands. When energy reaches the Earth's surface and causes it to vibrate, move up and down or back and forth, geologists use the term earthquakes for both the sudden movements that generates vibrations and the ground shaking that results when these vibrations reach the Earth's surface. In 1889, a physicist in Germany noted that a pendulum in his lab appeared to begin moving back and forth without having been touched. He reasoned that the pendulum was actually standing still while the Earth vibrated underneath it. A few days later, he read in a newspaper that a large earthquake had taken place in Japan about 12 minutes before the movement of his pendulum began. The physicist deduced that the energy generated by the earthquake had traveled all the way through the Earth from Japan and had slightly shaken his laboratory in Germany. Subsequent research revealed that the earthquake energy moves through rock or along the Earth's surface in the form of waves called seismic waves or earthquake waves. You can get a sense of what such waves look like by pushing suddenly on a spring or by jerking the ends of a rope. Geoscientists immediately realized that the study of seismic waves traveling through the Earth could serve as a tool for exploring the Earth's interior, much as ultrasound today helps doctors study a patient's insides. That's because seismic waves travel at different velocities through different materials. So by detecting depth at which seismic wave velocities suddenly change, geoscientists can pinpoint the boundaries between layers and even recognize the subtle boundaries within the main layers. This slide illustrates the layers of the Earth as we understand it based on seismicity. The properties are volume, percentage of the Earth, physical state of the material, depth in kilometers, density in grams per cubic centimeters, major chemical composition, temperature in Kelvin, and pressure in atmosphere. The average thickness is shown on the diagram on the right, as are the lithospheric and asthenospheric thicknesses. The crust is our home and the source of the food and resources that we use in our lives. This slide is a table and graph illustrating the abundance of elements, not minerals, but elements in the Earth's crust. The 8 most abundant elements are in decreasing abundance are oxygen, silica, aluminum, iron, calcium, magnesium, sodium, potassium. The chart shows abundance by percent weight, by percent volume, and by percent atoms. How thick is the crust? Well, in 1909, Andrija Mohorovic discovered that the velocity of seismic waves suddenly increased at a depth of a few tens of kilometers beneath the surface of the continents, and suggested that the increase was caused by an abrupt change in the properties of the rock. This change in velocity represents the crust-mantle boundary. Today we refer to this boundary as the MOHO. The thickness of the crust varies from 7 to 70 kilometers, with the continental crust thicker than the oceanic crust. There are two kinds of crust, continental and oceanic. The continental crust has a highly variable felsic to intermediate composition, with an average density of about 2.7 grams per cubic centimeter, and has a thickness that ranges from 25 to 70 kilometers. The continental crust comprises about 25% of the Earth's crust by area. The oceanic crust underlying the oceans has a mafic composition with an average density of about 3.0 grams per cubic centimeter and a thickness ranging from 7 to 10 kilometers, and covers about 75% of the Earth's crust. We base our understanding of the nature of the mantle and core from our studies of meteorites. We have also conducted laboratory experiments to determine density, the physical and chemical changes that occur due to pressure and temperature changes as we get deeper in the Earth. The mantle is a 2,820 to 2,890 kilometer thick shell that surrounds the core. The mantle consists of the ultramafic rock peridotite. The mantle comprises about 82% of the Earth's volume. The mantle is divided into two layers, the upper mantle and lower mantle. The mantle is divided into two sublayers, the upper mantle that extends from the MOHO to 660 kilometers deep, and the lower mantle that extends from 660 kilometers to 2,890 kilometers. At the lower portion of the upper mantle, between 410 and 660 kilometers, is the transition zone. Very decisive, step-like seismic increases in density occur within the transition zone. Because temperatures and pressures increases as we travel towards the center of the Earth, the mantle undergoes convection. The solid rock becomes plastic and undergoes slow convection, where hot rock rises or upwells and cooler rock sinks or downwells, as illustrated in the inset of a pot of boiling water. This flow takes place extremely slowly at a rate of less than 15 centimeters per year. The core is an iron-rich sphere with a radius of 3,471 kilometers. The moon's diameter is 3,474 kilometers. Seismic waves separate or segregate the core into two physically different spheres, a liquid outer core and a solid inner core. The outer core is comprised of liquid iron nickel sulfur. It is about 2,255 kilometers thick and has a density of 10 to 12 grams per cubic centimeter. The outer core is liquid because the temperature in the outer core rises so high that even its great pressure cannot keep the atoms in a solid framework. The liquid outer core convects both chemically and physically. The physical convection creates electronic coils parallel to the axis of rotation of the Earth. A byproduct of electricity flowing within the physical coiling convection is magnetism. The magnetic rays from this field extends around the Earth, protecting us from cosmic radiation. The inner core is a solid iron-nickel alloy created from the chemical convection of the outer core. As part of this process, iron-nickel precipitates as a solid onto the inner core, making it gradually thicker over the eons. The radius of the inner core is 1,220 kilometers and has a density of 13 grams per cubic centimeter. We can also regard layering based on rock strength. The lithosphere comprises the crust and the outermost mantle. It is rigid and brittle, meaning it breaks rather than bends. The lithosphere is broken into tectonic plates that we will talk about in detail in the next lecture. There are two types of lithosphere, oceanic and continental. The oceanic lithosphere is thinner with a thickness of about 100 kilometers. The continental lithosphere is thicker and ranges from 150 to 20 kilometers thick. The lithosphere overlies the asthenosphere, the plastic portion of the mantle that can flow and undergoes convection. The boundary between the lithosphere and the asthenosphere occurs when temperatures reach about 1,280 degrees centigrade and tends to be gradational and mimics the crust above. At this temperature, the peridotite undergoes partial melt. The partial melt occurs only in the upper part of the asthenosphere at depths between 100 and 300 kilometers, beneath the ocean floor. Most geologists place the asthenosphere at the top of the lower mantle.